Good morning. It's my pleasure to introduce today's first talker, Dr. Sacha Krstulovic. He has been done great contributions in the field of recognition of non-speech sounds in the context of smart cities. And the title of his talk is Sound is Not Speech, so I think this is somehow related to this work. Welcome.
Thank you, Thomas. Hi, everybody. My name is Sacha Krstulovic. I'm the director of AI Labs, which is the research division of a company called Analytic. Can you all hear me okay? Yeah? Okay. So the title of the talk is Sound is Not Speech. So speech is sound, sound is not speech. There's a bit of suspense and drama in there. I'm going to explain to you what I mean by that. But to introduce this talk, most of you have probably seen Google's announcements of their new range of made by Google products. This lineup of products is a good illustration of what's happening in the bigger picture of smart home products or smart personal products. You can see smart speakers, you can see a laptop, mobile phone, you can see a live logging camera, you can see a whole range of products, some of them for the home, doorbell, surveillance cameras, and so on. And that's paramount across all brands. You have Google in that sphere, you have Amazon, you have Apple, all the big companies. And you have a whole galaxy of other brands producing that kind of thing. Now, the interesting thing about the talk, Google's talk, was that the storyline about all these products was about artificial intelligence. The common point, the common denominator of all these products was artificial intelligence. So artificial intelligence, you have several types of problems that artificial intelligence is tackling. You have speech recognition, so speech-oriented artificial intelligence, speech recognition, speech synthesis, biometric voice recognition, sorry, for identity personalization. You have machine translation. Then you have image-oriented AI, which is in face recognition, video processing, and so on. Then you have another type of audio AI, which is music. So fingerprinting, for example, recognizing tracks, query by humming, and so on. Now, in my opinion, there was one missing piece to that puzzle, which is sound recognition AI, sound in a wider sense than speech and music. Enter audio analytic. For the first time, devices can intelligently respond to sound. What our company produces is algorithms and software for sound recognition. We were founded in 2010. We're based in Cambridge in the United Kingdom. And we have offices also in Palo Alto in the USA. We have about over 40 people right now, most of them being experts in machine listening, sound recognition, software engineering, and so on. And we're a venture-backed company. So we've been honored that Bloomberg qualified us an AI startup like no other, like a Shazam for real-world sounds, which is a simple way of explaining what is it that we're doing. Our active market focus is smart speakers and smart home devices. The value that we add to these devices is support for well-being of the family, loved ones, and so on. We have products such as glass break detection, smoke alarm detection, baby cry, a whole range of sound event detection products. But we also have expanding market focus in a whole bunch of areas. And the vision is that all technology will become context-aware through sound detection in the near future. Now, that was the kind of marketing side introduction of the company. But what I would like to talk about today is sound is not speech, as in what are the research challenges that sound recognition is facing, which are distinct, which make it a distinctive problem from speech detection or music processing. And there's a bunch of them. So first question is there a language of sound? Speech is bounded by language. So we could, for example, count the number of words in the English language. There's about 170,000 words, with a few obsolete ones, derivative, and so on. It's all countable. You can make new words, but it's going to be a small amount compared to the ones which are established words in the language. One manifestation of that is that old school, when you wanted to make a language model, you take the Wall Street Journal, and then you count the co-occurrences of words, and then there you have your language model. You might want to specialize it to dialogue systems and so on, but you can do that with simple text corpus. And if I ask you to complete a sentence, if I say hello, hello world. Most of you being computer programmers, you go hello world. Could have been hello Sacha, could have been hello Jonathan, could have been hello mom. I'm talking at the SANE workshop. But we can pretty much guess a number of legit endings to that sentence. So that's the kind of thing that, for example, modern end-to-end speech recognition is exploiting by predicting directly the sequence of labels from the acoustic sequence. Things like the CTC networks are aiming at modeling that kind of direct probability density between the labels and the audio. But can the same thing be done for speech? So if I ask you now, what sound will I make now? Any idea, anyone? Did you even know that you could do that with your mouth? Anyway, it could have been anything, could have been that, could have been this, could have been whatever else. And very little in the room, almost nothing in the room. You could argue, yes, but you have a mouth, you have a finger, therefore you can do that kind of sound. But it's very, very difficult. It's much harder, as you've seen now, to predict what sounds occur in a scene than predicting the series of words in language. So that's one of the problems that sound recognition is facing. Nonetheless, sounds are still communicative. Although there is no formal language in the linguistic sense, sounds are informative. And they are, a long time ago, I was looking to define classes of sounds in order to see which ones are more useful than others. And so I came up with a sort of taxonomy, which was the sounds which are crafted to communicate something, so intentionally communicative. Smoke alarms, your microwave beep or something, the car horns are designed to communicate something. You have incidental cues, which are sounds which are indicative of some precise event happening, which you might want to be informed about. So glass break informs you that somebody's breaking in. Vacuum cleaner might be informing you that somebody's there cleaning the room and so on. And then there are the more diffuse, more environmental sounds, which might not be directly related to human action. So aircon is arguable because someone might have switched on the aircon. But if it's an automated process of the building, for example, you might have aircon noise in the room, which is just there. And it's not necessarily related to somebody doing something. Babble noise of the same nature, wind, rain. And in the League of Environmental Sounds, some of them you might want to know about. You might want to wonder if you switched off your aircon before leaving or something like that. But some of them also are just noise. If you walk in the streets of New York, very soon you forget about the traffic noise, but it's still there. And the notion of generative model for sounds somewhat remains valid. So probability of smoke alarm given the sound of beep is something that you can calculate. However, there is one big difference, which is you're going to try to calculate the probability of smoke alarm given beep and lots of other things which might be happening in the scene and which might not be informative at all about the smoke alarm. I'll come back to that in a couple of slides. One thing which is another difference is the variety of production processes. So for speech, you have a resonance process. You have the vocal cords, which are exciting the vocal tract. Vocal tract is shaping the phonetic sounds. It's the similar thing for music instruments. If you take the saxophone, it's like a different type of vocal tract. You have the reed exciting the tube, and the tube is shaping the sounds. And it's going to be the same thing for most musical instruments. Most of them are exploiting the resonance phenomena. Now, if you look something like this is a glass break. This is us breaking glass, actually, in our test facility in Cambridge. We've broken hundreds of windows to actually study the sound of glass breaking and the real sound of glass breaking. That's very much more real than taking sounds out of Freesound or whatever online database. We did break windows with all sorts of glass thicknesses, glass materials, size of windows, and so on, to be really sure what this phenomenon was about. And so in nature, that's very different from resonance phenomena. It's a hard object hitting another hard surface. That hard surface is going to shatter. It's going to produce a kind of big, it's not a shock wave, but it's a wave which is very, very sharp. And then you're going to have the aftermath of breaking the glass, which is all the little glass pieces falling on the floor. And each of them going to have different sizes and so on. And that's going to be produce a very random, very specific sound, which has nothing to do with the resonance phenomenon. So if we explore the diversity of acoustic features, the nature of different acoustic phenomena, we have beep sounds. So that's a smoke alarm. That's a series of very simple tones with silence in between. Then that's one of our glass breaks. You can see very sharp sound with some aftermath. Violin is a harmonic phenomenon, but with very flat behavior in time. Baby cry is a mix of harmonic phenomena with some kind of variation of frequency in time, but you also have what's called the vocal fry in the middle, which is where the vocal effort of the baby puts the vocal folds into some kind of noisy kind of mode. And this simply is a vacuum cleaner, which is a shaped noise, white noise, and this one happens to have a hiss in the middle, which is a pure tone. So here you can see the diversity of acoustic phenomena we're dealing with. It's not just one phenomenon, which would be resonance with formants and stuff, just like speech. That's a very wide variety of acoustic production processes which lead to different types of features. Now, one of the questions is, should the acoustic features be handcrafted or learned? So this is our baby from before. Now, if I play that sound, can you guess what that sound is? Anybody? Was it?
Yeah, it's filters, very high.
Filters, yeah, it's filters. So the spectrogram of that sound is this. So we took the image and then we reverted it to playing sounds. That's a demo we did for the Science Festival in Cambridge, where we're asking kids, we had a touch screen and we're asking them to draw the harmonics and so on, and very fast what happened was this. They were drawing pictures or writing their names on the screen and listening to, oh yeah, that's the sound of my name. Right, so insofar as most standard acoustic features were invented by looking at spectrogram images, if image recognition can infer features, then why not? So sometimes we hear criticism, oh, convnets are image technique, why do we use that for audio rather? I don't have a problem with that, because actually there is such a kind of correspondence between what we see on the spectrogram and what we can imagine to be the acoustic features that, you know, why not? Why not? So another question is, are acoustic features enough? If you take our baby cry, or if you take this, which is an angry woman, you have you have the harmonics are still there, so that's a common between them. The pitch, the fundamental frequency is roughly in the same ballpark. So the acoustic features themselves might not be enough to distinguish between these two sounds. But if you look at the temporal evolution of one and the other, you might realize that the temporal patterns of baby cry versus female voices are very different. So there is a thing about the baby's lung capacity, for example, where they have to catch their breath between two episodes of crying. And that can lead to that kind of pattern interrupted with breathing. And so each and every sound is going to have its own temporal pattern, which is again related to the production process at the beginning of it. So temporal modeling might help. So as a matter of fact, if we look at the top systems, if we look at the task 2 of the DCASE data challenge, so the DCASE challenge is a comparative evaluation between sound recognition systems across 4 different tasks. Task 2 was the one which was detection of rare events. And those rare events this year were baby cry, glass break, gunshots, overlaid on a variety of background noises, street, park, and so on. So looking at the results of that, the top 2 systems, and many of the systems which were presented were actually blending several types of neural network approaches. So the 2 top systems were starting with, where's my laser? Okay, okay. We're starting from the Mel Spectrogram, which is a kind of raw, kind of not a lot of processing applied to the waveform. It's just extracting the frequencies across the Mel frequencies, which are related to the properties of hearing. And then they were applying some layers of convolutive neural networks assumed to perform some form of feature extraction. I will come back to why I'm saying assuming. Then both of the systems had a layer of recursive neural networks with LSTM units or GRU generalized recurrent units. Again, assuming that this is producing temporal modeling, which is really interesting. And then some simpler layer feed-forward layers with sigmoid functions to produce a decision at the end of the system of where the sound is in the recording. Yeah. So we started seeing a pattern there of systems which have these layers of feature extraction, temporal modeling, and then decision at the end. One of the things is like the DK's challenge in 2016 was presenting a wider variety of systems. There were still a few of the quote dinosaurs like the GMMs and support vector machines and so on. But actually, are these models really dead, or is it that they get less of the spotlight actually nowadays? That's a relevant question. So this year, we haven't seen that many alternatives to the CRNN approach, which I don't know. We'll see what happens in the future, but I believe in diversity and variety. So those systems are really, really interesting, but I think they should not kill other approaches. So another thing which is very specific to sound modeling is the notion of interrupted sequences. If we look at our smoke alarm again, it's that pattern is called the T3 pattern. It's standardized, and the standard for the T3 pattern is half a second of beep, then half a second of silence 3 times, and then another half second when you want to separate your 2 series of 3 beeps. But actually, it's not really silence. Those 0.05 seconds could be anything. If your smoke alarm is happening when you're cooking, for example, you have all sorts of cooking noises in the silence. Or if you have an aircon at your home, you're going to have a different background noise than if you're in a silent room like this one. So out of the 4-second sequence of the smoke alarm, 62%, 2/3 of the sounds does not predict anything about the sound itself. Whereas in speech, the contribution of silence, the pauses are fairly short. Or in music, same story, the pauses are fairly short. So there is, perhaps we need some kind of attention mechanism, modeling of the attention mechanism. This is a system which was presented in DK's 2016 by Mark Plumley's team. The interesting thing about this, this was neural network based. So we had the usual pattern of convolutive network with a recursion for temporal modeling and then the feed-forward neural networks for decision. But there were 2 extra branches. One was attention mechanism modeled by a simple network with sigmoid activations. And then another one was a softmax layer for localization of the sound in the recording. But I thought this one, the presence of this attention mechanism was really, really interesting. And that's probably something we need for the modeling of interrupted sequences. I think this year's system presented by the same team also, which ranked first at the weekly supervised sound recognition task, the task 4, also included a attention mechanism, and that's an interesting thing to notice. So another thing, if you look at 24/7 sound recognition, if you have a device, a camera or something, or a home assistant listening to what's happening in the environment 24/7, then the occurrence of the target sound, say baby cry or say smoke alarm, is much, much rarer, more rare than the occurrence of non-target sounds. So you have one sound which is up against a whole variety of sounds. If you live in a house with a family, you're going to have children making lots of different sounds. If you have senior citizens, they might be listening to the TV louder than other people and so on. You have a whole bunch of things which can happen, either generated by the house itself or outside of the home. So if you live close to near an airport, you might have aircraft noises, or if you're in a developing city, you might have construction building happening. So that gives you kind of like a visual hint that the target sound, the non-target sounds actually is a much, much bigger set than the target sounds. And the confusion matrix for that kind of problem would be one sound against an infinity of them. So as I said, the variability of the non-target set is very large. And that, for neural networks, poses problems of data balance. The non-target set being much larger than the target set. If you don't design some strategy for data balancing, you're going to have a network which is completely overwhelmed by the non-target information. So there are things there which are really interesting to solve in terms of data balancing problems. Now, you could also think of a completely different approach, which is recasting the problem as an open set recognition problem. And open set recognition proposes to model a ball around the target data and some measure of outlierism. So, but it's very early days for that kind of techniques. We've seen early results in vision and forensics. There is a very interesting tutorial by Rocha and Scherer in ICIP 2016. Which is just simply entitled Open Set Recognition Problem. Most of the models which are producing open set recognition are using support vector machines at the moment, because you can use the distance from the margin as that measure of outlierism. But we've seen also like neural networks with open set last layer, but that was more for multi-class problems, not for single class problems. So there is something there which is early days, but very, very interesting to think about. So back to all these neural network architectures, research is evolving, and we're seeing very clearly, I'm back from WASPA, so conferences like WASPA, but in general in artificial intelligence and signal processing research for audio in particular, a paradigm shift. So from the explicit modeling of phenomena, so MFCCs are capturing some of the properties of the ear and their spectrum shape model, or generative models like Markov chains, like speech, old school speech was a series of states and so on, which is mirroring the succession, the sequence of phones. Factorization and sparsity. So factorization was looking at extracting units, so just like musical notes, so units which are grounded in some kind of how to say object, acoustic object. There was an intermediate stage which was heavily data-driven DNN models. So bottleneck features, for example, was kind of saying, okay, now let's just assume that the neural network is going to capture features, but it was still a feature extractor, like explicitly a feature extractor. Or computing posteriors for feed-forward DNNs. So you were replacing your Gaussian models by something else, in that case, the feed-forward DNNs. And nowadays, clearly, there is something really interesting happening, is that DNNs are being mixed up and assembled by function, and so it's assumed that it's convolutive neural net. Well, convolutive neural nets are being used with the hope that they're doing feature extraction. Temporal recursive neural networks are there for the function of modeling some temporal evolution. Attention networks are there for the function of focusing certain types of modeling. CTC networks in speech are for the function of dealing with the labeled sequences. So now neural networks are not just one single animal. They're starting to become a Lego set where you can have several functions achieved by several architectures. But this thing is, for the moment, largely evaluation-driven. And very often you read in publications, or you hear people saying, assuming that the network architecture does X, evaluation shows that improved the rates by Y%. But for the moment, the certainty or the insight into the type of features that CNNs are extracting and so on is very early days. So we've seen work, for example, in Thomas' team for visualizing the type of features or that CNNs are extracting, or the type of things that RNNs are doing. So we're getting there. But it's not the same nature, it's not the same type of approach than what was coming earlier with explicit models of the ear, this and that. So because this is all evaluation-driven, data is a parameter, which is probably a good thing. I mean, this is data-driven, clearly, but we have to be extremely careful. When I say data is a parameter, what I mean is, okay, when we manipulate neural networks, we can manipulate the number of neurons, the number of layers, and so on. But also manipulating the data is a way to get the network to do something. Data augmentation, for example, is a way of using the data to craft. The manipulation of data has an impact on the capacity, capability of the network to achieve this and that. So that's something interesting. Data is not just there to learn. Data is also there to tune the system. You can put more data, less data, and so on. This is really interesting. So as I said before, there are some attempts at interpretation, plotting what the neural networks are doing. There is some grounding into, well, those networks were designed to solve problem X, Y, Z. But this could all be a massive horse. So we have to be extremely careful. When I say a horse, I refer to work by a researcher called Bob Sturm, who used the image of the metaphor of Hans the horse to talk about some music recognition tasks. Hans the horse is a horse in the, I think it was around the 50s. You can find the whole story on Wikipedia. Hans the horse was thought of as being able to do mathematics, perform mathematics. You would say, ask the horse, how much is 2 + 2? Horse would tap the hoof 4 times, and people were like, wow, this horse can do additions, multiplications, whatever. And there is one scientist, Dr. Fuchs, I think, or something like that, the guy with the lab coat on this picture, who started studying what's happening there. Is that horse really doing mathematics? And what he discovered with various experiments was that the horse was actually latching on people's reactions to the horse tapping the hoof. Which is something different than actually doing mathematics. So it was a simulacra. It was giving people the feeling that it was doing mathematics, but actually what it was latching on was something completely different. And it's not impossible that modern machine learning is doing that on some of these data tasks. So we have to be really, really careful about using a diversity of data sets when we evaluate a system. And researchers are very much aware of that. So we're going in the right direction again, but we have to be really careful that the system does not do something else than what we think it's doing. In the case of music recognition, the controversy was about a genre recognition task where it was proven that the neural networks were actually doing tempo recognition, and if you were shifting the tempo enough to throw off the results, but not enough to change the nature of the genre, that was proving that the networks were not doing the genre recognition, we're doing tempo recognition, which is a different task. So we need to be extremely careful about these things. I'm just going to talk about 2 more things which are of interest for sound recognition in the quote real world. So being from the industrial, a company doing products and so on, we need to be careful about a number of other things. Channel variability is one of the challenges of sound recognition. I'm going to play 9 different instances of the same sound recorded through 9 different consumer products.
Yeah, so, well, 2 years, I guess. 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 Yeah, so, well, 2 years, I guess.
So you can really practically hear the difference between all these devices. Some of them were removing the low frequencies. Some of them were boosting the low frequencies. You had muffled sound. You have clear, less clear, and so on. The 3 last ones had different types of noises happening. One of them was clipping the sound. The other one was adding white noise on top. Another one was adding a tone of electromagnetic interference. And so those are the things we have to deal with in the real world. Channel robustness in general is a very important thing to solve when you're doing sound recognition products. Another thing is about running on the edge. Speech may use cloud computing. What about sound recognition for consumer products? So running on the edge still has lots of value for that kind of products. First of all, it's a very simple form of distributed computing. You have billions of these devices in the field. And so that's like a massive, I mean, instead of buying the infrastructure yourself, you ask your customers to buy the little computer which is going to achieve the function of recognizing sound. That's a very good way to get rid of the privacy concerns, because the sound recognition being done on board the device, then the sound does not leave people's homes, so there is no question about whoever else is listening to it. It's happening on board the device only. Reliability is a thing, because if you remove the need for internet connectivity, then you remove one possible point of failure. And then real-time operation, you don't need to wait for the answer from your server for sound recognition. You have it directly from your algorithm. So those things have value. But then if you want to run an embedded system, you have to optimize the computational cost. And so one of the studies, so this is something we published quite a number of years ago, so it was still like old school systems, GMMs, SVNs, and then simple feed-forward DNNs or recursive neural networks. The point here is more about the methodology, as in the sound recognition accuracy comes at a certain computational cost, and in this diagram we plotted the equal error rate, so some measure of sound recognition performance against the number of operations that each of the tested machines involved. And we saw at the time that the GMMs were doing a decent job at classifying sounds at a fairly low computational cost. Support vector machines were all over the shop. And then neural networks, so the feed-forward ones, were having the best compromise between recognition performance and a number of operations, which was a simple measure of computational cost. So it's important to do that kind of thing for running on embedded devices. Right, so as a summary, I hope I made the point that sound is not speech, as in it's a different class of problems that we have to solve to perform sound recognition. So sound is not bounded by language or by musical theory. It can be anything. It's got that sheer variety of acoustic production processes and phenomena. So yes, just say the diversity of production process acoustic features. Then temporal structure matters, but it involves interruption. There is lots of things in the signal that we're processing that is not a good predictor of the signal that we're actually trying to detect. And also that problem of one against many. You have one sound that you want to recognize, and that's up against anything that can happen in a smart home. This is very important to keep in mind, and that triggers interest for data balancing and that kind of thing. Additional topics which might be similar to speech but are of interest for industrial impact are robustness to channel and room response. That's very, very important, because all these consumer devices were not necessarily as geared toward good audio quality as mobile phones, for example. And running on the edge matters for several reasons. Therefore, computational cost is a tangible question. Whatever algorithm we're going to deploy, we have to find ways of making it work in these devices. Now, because it's a new type of AI in its own right, with its own set of problems, there is also an interesting thing, which is that a new research community is forming around it. One of the manifestations of that is the book that we just came out. It's edited by Thomas Virtanen, Mark Plumley, and Dan Ellis from Google. Thomas Virtanen from Technical University of Technology of Finland, Mark Plumley from University of Surrey, and Dan Ellis from Google. And that gathered a series of authors. I've been very honored to contribute one of the chapters to this book. And this would be, today in 2017, the textbook about sound recognition. So I would encourage you, if you're interested in that kind of topic, to have a look at this. This is going to give you a very good idea, a panorama of all the things that are happening today in the world of sound recognition. I hope you found that interesting. If you, just plugging, if you are interested in that kind, if you want to work on these kind of problems, please join us at Audio Analytic. We are hiring at the moment. We'd be happy to work with many of you. Thank you very much.
Thank you, Sacha, for a very inspiring speech. So I'm pretty sure there is lots of questions.
You mentioned anomaly detection early on about one of the. So are you actually addressing that? Can you say something a bit about how your approach? Because it's kind of a difficult task in general. I'm curious about how you're approaching it.
Yes. So, well, it is a difficult task. There is also kind of controversy between definition of anomaly versus the definition of activity. I think it's very difficult to define what is an anomaly. I can't. I mean, I'm not allowed to tell you the detail of what we're doing, obviously, because that's our intellectual property, and we're a bit kind of protective of it. But essentially, yeah, anomaly detection. You need to have some form of adaptiveness of the system to your background, and you need to have a measure of what's out of the norm that the system would adapt to. So you can imagine all the fun problems on defining the temporal horizon of where you want to define the anomaly. But you know, customers seem to be happy with our product, so there we go.
Other questions?
This is not so much a question, but just to say, if anyone's interested in the book, then Thomas and myself will have a copy of it floating around today over the poster session.
So actually, I would like to ask, one of the challenges in this field that I find is that, like in speech, if you compare speech and environmental sound, in speech you have really clear or much more clear taxonomy. So speech consists of phonemes and words and so on. But if you consider environmental sounds, it's much more unclear what should be actually the labels that and environmental sounds can have very different meaning for different listeners. So of course, in a company working on specific products, I mean, that might be rather clear how to define those. But do you see any general approaches to this?
Yeah. So well. Insofar, it's funny, at WASPA there was a poster about recognizing how people would imitate certain sound like psh, bang, whoa, that kind of thing. So at Audio Analytic we have the notion of ideophones, which is sounds which are, you could think of them as phonetic units for sound recognition. And those phonetic units, again, are related to a taxonomy of various sounds. I mean, we have studies covering thousands of homes of what type of sounds are happening in them. It's a very large number of sounds. You can't necessarily, how to say, count all of them, but you can establish a kind of taxonomy of which ones are produced by humans, which ones are related to this and that production phenomenon, resonance versus noise versus this and that. One of the approaches for labeling is one that you guys came up with actually, which was really good, which is always including in the label the object and the action, as in I don't know, woman singing, woman shouting, coffee grinder grinding, vacuum cleaner humming, buzzing or something. So that was a really good way of defining this kind of taxonomy and having some notion of labeling which holds. One of the things, I mean, we're all having the same problems in terms of sometimes it's difficult to find the end of the sound for some of the sounds which are continuous. That's very true for environmental sounds, like when does the car finish passing. For home sounds, smart home sounds is a bit less the case. Many of the sounds are sort of discrete, have a fairly easy to define beginning and end. So maybe it's less of a problem for indoor sounds than outdoor sounds, I think. Yeah.
Okay, thank you. Let's thank Sacha again.